We tend to do a lot of RF welding. I'd say that's definitely the thing we're invested the most in. And it's largely because it's a very flexible technology, and we can oftentimes shorten lead times for things like tooling, and the tooling is oftentimes less expensive. But there are times when it is totally necessary to start looking at some of those other options, such as thermal contact welding, impulse welding, ultrasonics, etc. I would say sort of the first real thing is customer requirements and end use. That's really kind of what drives the decision initially.
Thanks for joining us for another episode of Inspiring Innovation. Today we've got a real-life engineer guest and somebody who's been a valuable add to the Polo team. Derek Severson is with us today, and Derek's been instrumental in a lot of our RF sealing launches and really gets into the technical details. Building the tooling, working through the design for manufacturing, and just a wealth of knowledge for our team. So we're excited to have you on the podcast today, Derek. Thanks for joining us.
That's my pleasure. Like Sean said, my name is Derek Severson. I am a project engineer in the product development department at Polo. So I'm kind of at the pointy end of the stick when it comes to new products and product launches, designing and building our manufacturing processes.
Yeah. And Derek, to that point, I mean, it's a pretty cross-functional team, right? We've got quality involved early. We've got project coordinators. We've got our salespeople. We've got designers. We've got project engineers. So what point do you pick up in a program when we start getting customer information to start quoting something? Where do you kind of jump into the picture, and what's your role in throughout development? Kind of walk us through that.
So we get involved pretty early as project engineers. Typically it's right after sales has went through and received an opportunity from the customer that they think looks good. That usually passes then through my manager. They check it, make sure it's a good fit, and then it gets passed out to our project coordinators, and they assign a team to it. We assign a project engineer to every product that comes through product development at this point. Our level of involvement kind of depends. The sewn goods primarily go to our product designers, but we handle tooling, fixturing, things like that for them on those sewn goods, and we do work with them on them to an extent, but the bulk of our job is contained in our sealed products. So once the opportunity comes to us, then we normally everything at Polo starts with a quote. So we typically start with a budgetary quote, look at the product, you look at the information from sales and that the PCs have received from the customers. And then we go through, evaluate it. If need be, we'll go back to the customer and request more information if we don't think it's sufficient for us to actually be able to get a somewhat accurate quote out. Then we go through, build our quote. Our sourcing team goes through, finds us material pricing. We go through, we design our manufacturing processes, we put together tooling estimates, and it's really kind of a reverse engineering problem on the engineer side because you have a completed product typically. Sometimes it's a more of a design focused project as well. And you go through, figure out how to make the thing, and then we produce our quote, and that goes out to the customer. From that point, ideally, we move into our sampling phase, and that's usually when we'll open up tooling if need be. We'll go through, we'll get materials in-house, we'll build sort of initial samples, depending on what the customer wants. First samples are really kind of a problem-solving time for us. You go through, see if your tooling is going to make sense, see if this is something you have to change. You know, I may need a fixture here, I may need to redesign how I'm locating this part for this tool. That sort of thing. We also then kind of get quality involved at that point. Quality is involved to an extent in the quoting process, but once you move to sampling, that's when their involvement gets a lot more in depth because they sort of figure out then, okay, do we need this to be something that's validated? What do we need from our end to make sure we're all good here? You know, do we need additional fixturing in here because there's critical quality attributes that the customer is requiring? What's this testing going to look like? Things of that nature. So From sampling, then we go through any validation that we need to do from there. We may rebuild samples if we have to correct something or we wanted to make a change. From there again, we go into building our work instructions and our bill of manufacturing. Then we move into first production. I'm still involved all the way up through the first production, and we don't actually have a formal handoff all the way to production until after first production's been completed. We go through, we have a post-mortem meeting to determine if there is additional development work that needs to be done before a full handoff occurs. If production feels like they can take it without a problem, then that gets passed off to them, and then that kind of goes off my active project load. Now, if production doesn't want to go through, do a redesign, get more information from the customer, things like that, I can end up getting involved again later, but generally after that first production is sort of where that handoff happens.
Yeah, and how much are our plant engineers involved in some of the work leading up to the production launch, and how do you kind of bridge that gap from development to production in terms of like even what goes into the BOM or what may need to be added or tweaked or settings on a machine? What kind of stuff are you guys collaborating on with the project or with the plant engineers?
Yeah, so the plant engineers, one of the things we've been trying to push more and more since I've started is trying to ease that transition even more than we had previously. So it sort of depends on the product. Depending on how confident we are it's going to go into production, when it's going into production, that all sort of depends on where we start getting our plant engineers involved. But say it's something that we are confident is going to go into production, we're going to have plant engineers involved as early as, say, our very first tooling meetings when we're going through our initial tool design for samples. That's probably the earliest that they really get involved. But if it's something that's, not fully designed, we're going to have to go through a couple of revisions. We may ask for their input on a couple things here and there, just depending, because they're really valuable resources for us. But yeah, kind of right around when we start launching tooling is sort of when they get involved at first.
Gotcha. Yeah, thanks for that explanation. That was a good, thorough walkthrough of a long development process with many moving parts and pieces. So appreciate that. When we get early into a project, usually we'll get some kind of tech pack or drawings. And so, sometimes we get 2D prints, sometimes we get 3D prints. We talked about different files like DXS files, DWG files, step files, and sometimes we get a physical sample. Sometimes those things don't all agree with each other. And so how do you work with our customers and what do you do when some of the inputs may be incomplete or sometimes they contradict each other?
So typically with that is it's, especially as we're starting to really move in toward the sampling process, we start digging deeper into what we've been given from the customer. A lot of the time it's sort of PDF drawings. That's probably the most common thing we get. And then usually, especially with sewn goods, seems to be, you get a physical sample. For a lot of our customers, they're not the ones actually building the physical samples. But they're the ones developing the drawings. So we do sometimes see mismatches between those two in terms of tolerancing or even construction method overall. So typically when we're doing this, probably the first question that we're bouncing back to the customer is, so do you want us to, here's what the differences are between your sample and whatever other inputs we've been given. What do you actually want us to build to? And then with that in mind, we may have them go through, update their drawings. We'll usually provide red lines if that's something that's necessary. And then we can kind of go back and forth with the customer on that as to what they actually want us to deliver to them when those sorts of inputs are not all in agreeing with each other.
Well, and another thing that I think is common, especially with sewing goods, like you said, is needing different sub drawings. And so what's usually the reason that comes into play, that we need a different sub drawing to support something that we got initially?
Sometimes we may not have the sub drawings.
Right.
And when you don't have the sub drawings, you're kind of just looking at those top levels and some details might not be clear. The most obvious example I can think of is sometimes we get very We get quite complex products that come in with sewn goods that are harnesses, carrying equipment, things like that, where you have stuff like belt routing and the way webbings are intended to go through all these different pieces of hardware. And when you're just looking at a top level, that isn't necessarily something that's going to be all that clear. You kind of need some additional section views and detail views and things like that to actually make sense of what's happening in the drawing. Yeah. That's one of the advantages of actually having a physical sample, of course, is that does give you something to cross-reference to, and you can kind of start to pick apart what's actually happening in the drawings if they're not 100% clear.
Sounds about right. You mentioned a lot of experience with our RF welding, and we do offer other capabilities for different methods of sealing, whether that's RF, impulse, ultrasonic, thermal contact. You know, we even do some thermoforming in one of our locations. How do you decide which joining method a product needs, and what might disqualify something from being RF? Or are there certain materials, or I guess what qualifies or disqualifies something for RF, and how do you decide the proper joining method?
We tend to do a lot of RF welding. I'd say that's definitely the thing we're invested the most in. And it's largely because it's a very flexible technology, and we can oftentimes shorten lead times for things like tooling, and the tooling is oftentimes less expensive. But there are times when it is totally necessary to start looking at some of those other options, such as thermal contact welding, impulse welding, ultrasonics, etc. I would say sort of the first real thing is customer requirements and end use. That's really kind of what drives the decision initially.
How about like materials? Like, I know that there's some technical terms that go a little bit above my head, like polarity and bimolecular structures and things like that. Can you give us a much more scientific explanation to how that works?
So one of the big reasons you might disqualify RF welding from building a product is the required materials being used. RF welding only functions with a certain number of materials, particularly polar plastics. What that essentially means is that you have a molecule, it's got a positive side and a negative side that are charged differently. And it's only when you have those sorts of polar plastics with oppositely charged dipoles that the RF can actually excite the plastic in order to generate heat and actually make a weld. So if you don't have a polar plastic, that immediately disqualifies RF as an option. But that's not necessarily the only reason. We've ran into some materials in the past that have, for example, carbon black as an addition to the plastic. You can heat carbon black to an extent with RF, but it makes using RF welding far more difficult. So that's something that we may end up going to something like impulse welding for, just because the additives to the material are making RF welding just not as reliable of a process as what we need. I would say probably the other big reason to move away from RF welding is if you're welding sort of incompatible materials, or you need to use something like a heat activated adhesive. That's just not something RF welding does very well. So you kind of start looking more toward thermal contact and impulse for that sort of welding.
Can you talk a little bit too about the differences between RF welding and impulse welding, just the mechanics behind it?
RF welding is you're kind of directly exciting the actual molecules of the plastic. They work the thing that's most common that most people know about, that's most similar to RF welding, is a microwave. Because the way a microwave works is it just excites water molecules to generate heat. RF welding pretty much works the same way, except you're exciting plastic molecules and you have a die so that you're only exciting the molecules in a certain location of the plastic. Impulse welding, it's kind of more similar to, say, a coil stove. You have an electrical heating element, you feed electricity through it, and the resistance of the element generates heat. With impulse tools, typically you'll have your element, and then it'll be sitting on like a water-cooled pad, and then you have some way to deliver pressure with also another water-cooled pad, basically, so that you can quickly heat up your element, melt your plastic, and then the water cooling brings the temperature of everything back down under pressure, so you make a good, strong bond.
Nice. Yeah, I appreciate you also making me hungry during this podcast with microwave and stove references there. That, but it really does help us think about those different methods of sealing, and so I appreciate that explanation. Let's go into sampling a little bit more. So going from a one-off sample to repeatable production processes and designing for manufacturability, where do a lot of programs struggle? How do tooling lead times, die design, and just kind of the sheer number of validation permutations decide whether something that worked can actually be replicated at scale?
Sort of that scaling from a single sample up to actual full production can be extremely difficult. Your tooling, with sample tooling, we can oftentimes get away with things that are a lot more difficult to actually locate accurately. You know, when you're having an engineer run the parts and they're only running a couple at a time, you're able to pay a lot more attention to how things are aligned and how your material stack up's working. And you're able to sort of go through and smooth out those processes to kind of make a few good products. Now, of course, when we go to full production, it's unrealistic for us to expect our operators to be putting that much time and attention into an individual product. And even then, that's not a very controlled process. So that's when we started looking into doing things like including more fixturing, go, no-go gauges for doing quality checks, changing the way that we're locating materials on the actual tooling, and things of that nature. Multi-up tooling, that's the other thing that sort of starts getting looked at depending on how high of quantities we're running. So we may go from, you know, especially with something that's not a very well proven design, we may have started with something that's only making a singular product in one shot on an RF welder versus something that's, say, making 4 or 5 at a time, and maybe you now have 2 different trays so that you can run a turntable or some other kind of machine that's going to help increase your throughput. So that's sort of the things we started looking at. Now, sort of how your tooling lead times and validation, stuff like that start to get involved there is, I think, probably the most common thing to happen is that your tooling and material lead times, which can both be very long depending on what specific processes you're using. Probably the biggest way that can start to impact that sample to scale process is that it just cuts the amount of actual development time and the amount of hands-on time we have with these particular materials on these particular tools. Because that's really sort of where we learn the most about this particular production process. With sealing especially, you kind of have to treat every single product, every single material, every single tool as their own distinct entity, because they all require different things to actually make them function properly once they get out on the production floor.
Yeah, that's great. You know, one of the first steps in any development process is cutting. So can you walk us through some of the decisions that you make there? When is it necessary to use a die cut? When do you use a laser cutter? When do you hand cut a part? And what's some of the trade-offs when it comes to accuracy, speed, or cost? You know, is there a time that you rule out if hand cutting's even viable for a sample?
For sampling, hand cutting does happen sometimes. We still try and avoid it because it's not 100% production representative. We have some of our own dedicated equipment and product development now to help us get something that's more production representative and also help increase our throughput when it comes to building samples. With hand cutting, it does occur occasionally, even in production. Things like trimming off pin locators does happen sometimes with, we have in the past built products where we had contamination concerns with some of our other equipment. So we kind of isolated those in a different place in the building and we hand cut the parts because it was fairly low quantity. That's happened in the past. But hand cutting is not something that Polo really does anymore just because the other processes have better throughput, better quality, they're more repeatable, and they're just generally more accurate. Now, sort of where die cutting versus, say, a CNC knife cutter or a laser cutter comes in, that gets to be a little more complicated. That's largely driven by, I would say, 2 things. One is the material type that you're cutting, and the second thing is the precision requirements. Electra or CNC knife cutting is easily the least expensive in terms of labor, because now we're talking about something that can cut, 10, 20 layers of a single material. in a single pass. But with that increased speed, you have only a limited number of materials that really work. Generally, only breathable materials are going to work well for an application like that. Also, if you have things that have really small geometries, especially internal geometries, that's not necessarily where that cutting technology does its best. And also just overall precision can start suffering. When it comes to a sewn good, usually we're able to hold plenty good enough tolerances on that, that your seam allowance and everything else, it all comes out just fine. But when it comes to RF welding and more sealing operations, where we're maybe pin locating parts and you require things to be better stacked, that's when we'll start looking more toward laser cutting or die cutting.
It seems like there's a lot of benefits when it works out for the Electra or some of that automated cutting where the designs are very intricate. It seems like there's probably benefits to less scrap because you're getting as much out of that material as you can and tons of efficiency.
Yeah, 100%. Die cutting, your main benefit is precision. You can run non-breathable materials through it without a problem. You can cut, depending on the material and depending on the style of die, you can cut 10 or 20 layers on it. So there's some advantages there too, but in terms of material scrap, and especially if you have really complicated geometries, it gets really difficult for an operator to be able to nest that die in more complex fashions, whereas the Electra, that's just not a problem.
Let's just say in a perfect world, when you're moving from sampling and you've got an approved sample, how would you kind of characterize the process from there when you're kind of trying to get more of a consistent, repeatable process, as you've mentioned, for production, where you're maybe dialing in your power or seal time windows or finding worst case settings that still yield a good part? How does that process look like before we move into production? But before we get into that, this podcast is brought to you by Polo Custom Products. We are a custom manufacturer that specializes in sewing, sealing, and thermoforming. We work with project engineers, sourcing professionals, and buyers to design, engineer, and manufacture products that cannot afford to fail. If you're interested in working with us, visit our website at www.polocustomproducts.com and fill out a request for quote form. Now, back to the show.
Yeah, so it sort of depends. Characterization or process characterization is something that's an official one, I should say, is something that's more reserved for our medical products that are going through a full validation process. Now, even for the rest of our products, we oftentimes will build multiple samples of them, especially if we're planning on changing any of the processes or we're changing tooling off of, compared to what we did for our very initial samples, be it for repeatability or speed. So we may go through and build some additional samples there. When it comes to sealed goods, primarily sort of what we start with for process characterization is we're going to take whatever we used for sampling. We're going to kind of use that as a reference, and we're going to go through and make any changes we need to make to things like our buffer stack up, or if we need to modify a die or move to a different machine to get something that's more stable, that works better, that's going to be more production representative. In case of machines, process validations are generally restricted to a singular machine and a singular tool. And once we've done that, then we kind of go through the process of deciding which of our sealing settings are the most important, which ones can we kind of leave as a stable setting, something that we're not going to change, and then which ones are real variables for the sealing process. So once you decide on what your variables are, you're going to set all of your constants to wherever you think they need to be. And then you go through and you kind of just run through your range of settings for whatever your variables are. You do 100% testing, usually destructive testing, and kind of see what your results are there. And then once you sort of really get a good idea of what a really nice, stable range of settings for your variables are, that's when you can start then moving toward an operational qualification or a process qualification for full validation when it comes to medical products.
Well, and there's a lot of talk around DFM and designing for manufacturability, and our customers do look at us, I think, for some tips and pushback even on some of their designs, and that could be heavily engineered and but maybe not as practical when it comes to manufacturing at scale. So I wonder how that translates. I mean, you've talked about die heights, step dies, buffer material on a stack. Where do you see small design tweaks that can make a real difference for high volume manufacturing?
The things you were kind of referring to, that's more tooling design, and that's something we generally keep in-house. We don't have to bounce back to our customers for, but those can absolutely kind of make or break a product if you get them wrong. But when it comes to more general DFM, those are sorts of things where we're going back to our customer and saying, hey, this is either going to, can we drive a cost saving here? This is going to be a more, repeatable process for us. We're going to be able to cut out, 2 or 3 processes if we do it this way rather than this way. And that's sort of more so where the DFM comes in. For example, I had a customer with a medical product that I worked with recently, and they, in their drawings, they had these bladders that were designed that were then put into an overall shell that was sewn. So these bladders are not something the customer sees at all, but the way that they had them designed was such that they were showing seal bead all the way to the edge of the material. And these are intended to be RF welded. Well, RF welding doesn't really work very well when you're sealing right to the edge. So normally for a process like that, if we actually wanted it to be sealed all the way to the edge, well, then I'd have to go through, I'd have to seal it, then I'd have to add some kind of secondary cutting operation to then remove that so you can get a good, clean, welded edge. So instead, I went back to the customer, said, hey, so these are kind of our 2 options to look at this. I can either go through, add that secondary cutting operation, probably add cost and make it a less good process, in my opinion, because now you're introducing another potential failure point and another thing that can be screwed up in-house and potentially cause a leak in that bladder. So instead, I proposed that we just narrowed the seal width, kept the internal volume the same, and that left us enough clearance from where the seal bead ended to the edge of the material to where now the RF welding works. I don't need a secondary cutting operation, and it's still a product that's going to meet our actual customers' expectations and do what it's designed to do.
That's great. Yeah. Well, can you walk us through tooling as well? So there's different pros and cons for things we might do in sampling versus we might do in production. There's costs, there's lead times. So how do you look at when to use aluminum versus brass or a wood back versus a forged die? How do you look at those things when you're in the developmental stage, or do you just come out of the gates with a forged die? What are you thinking through the development process versus the long-term production solution?
A lot of those sorts of things are you're kind of start to balance basically your lead time versus the long-term durability of your tools, as well as cost. So for example, with dies, we generally do either like wood back steel rule dies, which are very fast, very accurate. They're really good for complicated geometries in terms of being able to bend for small features and things like that. And we can get them in-house really quickly. The lead times are just a lot shorter for them, and they're a lot less expensive. Versus you start looking at like a forged heavy duty die. Now you're more design restricted. It's a far more costly die. I would say 5 to 6 times more expensive probably, but they last far longer. You don't have to be as concerned with what materials are cutting. And for us, we're able to usually cut more layers of material at a time. So you get some labor savings in there. And that sort of depends on, say, the quantities of what you're doing, what's the design of the actual part, because, even if it is a high quantity part, if the design's complicated enough, we may stick with those wood back steel ruled dies versus a forged. And then when it comes to RF tooling, you kind of alluded to brass versus aluminum. Generally, RF tools are kind of very similar in construction. It's usually an aluminum plate, and then you have just a sort of a base to build the die on. It has your locating features and things like that. Then you have the actual physical die, that's your seal edge. What's the actual shape of your part? That's what's sealing it. That is generally either aluminum or brass. I have heard of people building dies out of things like magnesium or even zinc-coated steel.
Wild.
Yeah, that one's a little crazy. I found that in an old book that our RF press manager had.
Nice.
And then the bottom tray is just another sheet of aluminum with whatever your part locating features are. So the main advantage of brass is it's just a lot more of a durable tool. It may sound kind of counterintuitive because brass is pretty soft, but in an RF welder, one of the big risks you have is you can cause actual arcs, kind of like welding, right? You can start a physical arc because of how powerful these machines are. They do have protection features in them to prevent you from totally destroying your die or causing other problems, but you can end up with some die damage from that. The advantage to a brass die is generally they don't get damaged. They're not as likely to get damaged. They're easier to repair if they do get damaged, and they're just a lot more forgiving in that way. Whereas aluminum, generally just not as durable. They're not as likely to do well if the machine does arc, which is always a risk with any RF welding process. But there are some advantages to it. It is less expensive. It's easier to machine. And there are certain circumstances that really make it kind of a necessity. Occasionally you end up designing tools where the particular loading process of the tool makes it necessary where you have an operator now handling the physical die. And in that circumstances, for the sake of ergonomics, you will oftentimes go to an aluminum die just because you don't want just due to weight concerns for your operators. Probably the best example I have of that is we've done some dry bags in the past where you had basically a solid piece of material and you're taking it, folding it over itself, and then you wanted to weld the seam on the top. Well, you can't just have a normal die coming from the top because then you'll weld through the whole material and then you end up with sort of a figure eight shape. So instead what we did is we had a removable bar with a piece of insulating material on the bottom. So we laid in our layer of material, we put in the bar with the die, and it had some contacts in there so it could still go to ground in the machine. Then we folded over the lap seam on the top, and then we had another die that came out the top. So you still got power ground, still made your seal on the top, and you didn't cause a weld all the way through to the bottom. And in that particular circumstance, that bar was aluminum because our operators had to be able to pick it up and maneuver it easily.
Interesting. And Derek, remind me, is your background mechanical engineering?
Yeah, so I have a degree in mechanical engineering from South Dakota State University.
Okay.
I also have a specialization in aerospace engineering.
Okay, nice. That's served you well at Polo, and you definitely have a great technical understanding of our processes, and so I appreciate you sharing that with us today. One more kind of topic here. Well, I guess we still got a couple left, but I wanted to talk about our bill of manufacturing. And sometimes, if there's anything that we can trace back to an issue, it's something we need to add into the bill of manufacturing, or maybe we missed a process setting, or it wasn't like a design issue itself. So how critical is getting we call it a BOM. I don't think that's necessarily custom in the industry, but how important is getting the BOM right, and part of how critical is that to the kind of cross-functional process and handoffs that take place when we're going into production? So
for Polo, yeah, as you alluded to, we refer to them as BOM. That is not necessarily industry standard. BOM typically refers to bill of materials.
Right.
For us, our BOMs are our bill of manufacturing, which contain a bill of materials, and they also contain our work instructions, processes, rates, things of that nature. So the integrity of that and making sure that you have all the information you need in there for your operators and for the engineers and our scheduler is extremely important. If you kind of have things that are missing in there, you can end up with bad product at the end due to missing things like certain quality checks, or things may be done out of order. If instructions are not clear to the operators, you can run into situations where they're we talked earlier in the podcast about running webbing for buckles and stuff like that. Mm-hmm. Well, if the drawings are hard to read and they can't see how it's supposed to be done, then they're probably going to do it wrong. So those are sort of the important things in the BOM. Now, when things are missed, that does happen. Probably the most recent example for me is I had one recently where it was a validated product and my processing settings in the BOM were all correct, but I had missed out that the machine it was running on had a step start function, which I had neglected to put in there. So my setup manager, one of the engineers, was trying to get this to run on the machine, and it's like, well, it's not sealing. And so they brought me in, I looked at it, checked the settings. So that all looks right. I look at the part and I can tell it's not getting enough power. So I go, well, hang on. let me check something. I walk around to the back of the machine, flip the step start switch, and then it starts working as intended, which is now going to be part of a product alert to get that updated in the BOM. So those sort of ECN processes, our internal changes to the BOM, all of that's really important to make sure that we're getting that feedback from the production floor for things that need to be added into our work instructions. If, the manufacturing engineers feel that they need to have another shop aid or something like that, or we need to make a rate change, all of that needs to be captured in there. And then same thing with our ECN process. The ECNs for us are just customer driven versus internally driven. So again, if our ECN process isn't put through, or if our customers don't put in an ECN for something, which we've actually had happen before, well, then we don't know about it and it doesn't happen. And then we're not making the correct product for what the customer's expecting because they never told us that something had changed.
Well, I think this could go for our customers along with our sales team and our outside reps sometimes too. But what do we consistently underestimate when it comes to the timelines for development, and whether that's tooling, lead times, validation scope, different types of validation that could have completely different requirements, whether that's for a major medical OEM or, an aerospace customer? What's something that we consistently underestimate that takes that's time consuming in that process?
There's several things. I think sort of the big ones that come to mind for me is number one is material lead times. Mm-hmm. Polo has a very robust supply chain team in it. We source the vast majority of the materials for our customers, and they oftentimes don't realize that some of these materials can have things like 14-week leads on them, which, when we're talking about product development, I need materials so I can build samples, and, some materials you can't get sample material for. So that can push back the entire chain of events for development substantially. And that's something a lot of customers don't sort of realize. I think probably the other one is tooling lead times. We have the ability, because we do a lot of our tooling in-house, we can sometimes are able to sort of bring in those timelines and get things done faster than if we were having it all outsourced. But, we still need materials in-house. It still takes design time to do these things. And a lot of customers don't have a really good idea of what that actually looks like. You just brought up validation. Process validation is the way we run it at Polo is extremely robust when it comes to actually having something that's going to be making good product once it reaches the production floor. But because the testing is so robust, it does mean that you can end up in a situation where your lead times for validation aren't what we expect, because we did run into an issue that we weren't expecting, and it took longer than expected to actually go through and fix the problem so we could move on to the next step. That can happen, and process validation in general is very time consuming and can be very costly in terms of time and material, because a lot of the time you're 100% testing, and a lot of the time those tests are destructive. So I think those are probably the big three. The other one that gets some customers kind of neglect is how long it actually takes to build things like work instructions. Good work instructions are, that branches into a very specific type of technical writing. And to be able to clearly explain to somebody how to actually do something, and with both words and visuals, is something that's actually very difficult to do well. And it takes time to be able to do it. We spend quite a bit of time working with our BOM team to be able to build something that's going to be very readable and very easy for our operators to follow, so that they have the best chance to actually successfully build product that meets our customers' expectations.
Can we call the BOM team the BOM squad?
The BOM squad. I've definitely heard that one thrown around.
Yeah, I know. You've probably heard this story before, but that one of our colleagues was on the phone saying, "Get the bomb ready," and then they were pulled into security at the airport for.
I did not actually hear that.
Yeah. Well, apparently they were flying into DC, so if you don't think our phones are monitored, they certainly are, because he was pulled into a back room, everything was searched, and he made it eventually, but had a lot more anticipated. A lot more than he had anticipated going through security that trip.
Sounds like it.
Yeah. Well, so last but not least, a lot of our customers are determining kind of a make versus buy. What are they going to bring it in house and maybe learn this capability, or are they going to outsource it to somebody that's like us, a custom contract manufacturer? And so what do we, what's our in-house depth, whether that's, what we can do with tooling, with multiple welding methods, with, validation, all being under one roof. What value do we provide that they may not consider when they're going through that exercise of, well, we just purchased these things and, we'd be able to run that and look better on our books?
Yeah, I think probably the biggest things that sort of Polo brings to the table is we're sort of a one-stop shop in a lot of ways. We have a lot of customers that kind of just drop designs on our desk, and we go through, we source all the materials, we design all the tooling, we source all the tooling ourselves, we figure out all the quality processes on that. We work with them in terms of quality requirements and compliances, and we kind of just handle it. That's a really big thing that we bring. I would say another sort of big thing, especially with sealed products and sewn actually, is we do a lot of our tooling in-house. That is not something a lot of places sort of actually offer. And in terms of RF tooling, there's only like 2 people in the entire country, a handful, that actually build RF tooling. So if you go to other contract manufacturers, they're all buying their tooling from the same people, whereas we actually have the ability to make our own tooling in-house, which allows us to go through, make modifications if we need to do them. We can implement design changes more easily, and we can cut down a lot of the lead times. So I think that those are 2 real sort of big advantages we bring. We also have the ability to be really flexible. Things like that in-house tooling really makes it so we can very quickly pivot when we need to. I had a project recently where we were on a very aggressive timeline with it. I had just gotten my materials basically, and we found out that we didn't have one of the materials and it was being brought in from overseas. Well, we were able to pivot with our design team. We have people on the ground in China who were able to then go to the material supplier, get us sample material that was sufficient for me to build these samples, get it on a plane and flown over to the States, all within 48 hours, essentially. And then coupled with that, I had also built some samples with not the correct materials because I didn't have the correct materials. And we found that, this tooling method that I'm using isn't actually going to work the way I had hoped. Well, we were able to very quickly pivot, redesign all the tooling, had it made in-house, and I was building samples again on site at another production facility in 3 days. And that's not something a lot of other companies can pull off, but that's something Polo can do. We don't like to do it. That's very stressful.
No.
And it brings a lot of risk to it. But I think that just kind of shows how capable we are as a company due to the fact that we have these really robust teams here. Yeah. We have a supply chain team that can really make things happen. We have our own in-house tooling, so if we need to do a redesign and we need it fast, we can pull it off.
Yeah, it's a great example of going above and beyond for a tight timeline for a customer, and I know customs got involved in delaying that timeline, and still yet you all were able to deliver on the dates that we had proposed up front. So it's really incredible to see the team and how hard y'all work. And Derek, I feel like this was probably the most technical podcast that we've had so far, which I'm thoroughly excited about, because who we're trying to reach is our project engineers at our customers, our product managers, the people that would really enjoy and interact with this content. So I thank you, because it's not just as you said, with technical writing, that's kind of a rare skill and not easy to do. And so technical communication is not easy to pull out of people, but had a great time training with you and your team in Monticello, and really wanted our audience to hear your expertise, and you did a great job today. So thank you so much for joining us on the podcast.
Yeah, thanks for having me, Sean.